Swayam Prabha. Digital India. Educated India.
We begin this lecture by discussing about irrotational and rotational flow, and that will be followed by discussion on strain of a fluid element, and subsequently we will discuss about some integrals which will be useful mathematical tools for our entire course. So, the concepts that we will cover here include vorticity, rotational and irrotational flow, strain of a fluid element, gradient, divergence and different integrals including line, surface and volume. So, these are the key points of this lecture. So, let us continue where we left the last lecture. You may recall that we discussed about curl of the velocity vector, and prior to that we had discussed about angular velocity of a fluid element. So, we had discussed that angular velocity has three different components: omega x, omega y and omega z, and since curl of the velocity vector is 2 times angular velocity, therefore, curl v is also a vector comprising of 3 components. So, let us call curl v as omega, capital omega, and then we can write down its components. Let us write down omega x, we can call this as omega x, omega y and omega z. This is the nomenclature we are following in the course. So, these are the 3 components. So, this is omega y and this is omega z. So, you can imagine that in the 3 dimensional flow field where all the 3 components exist, and then you are trying to look at the omega vector, it may be pointing in a direction which will be governed by the components. You may call this as the omega vector. So, the fluid element may be following a streamline, but the omega points in a different direction in space. It may or may not be aligned in the streamline direction. Now, as we follow the fluid element, we move to different parts of the flow field, and in different parts of the flow field, the velocity vector has different components u, v, w, and as we see different portions of the flow field, we are moving through regions where the velocity is changing continuously as a function of space, and if it is an unsteady flow field, additionally as a function of time. So, here what you see is spatial derivatives of velocity components. Which form the different components of omega, whether you are talking about the lower case omega which stands for angular velocity, or the capital omega which stands for the curl of the velocity. What happens if curl of the velocity vector is not equal to 0, it gives rise to a rotational flow, and when it is equal to 0, it gives rise to irrotational flow. Let us try to understand the implications. So, rotational flow of course means that you have a non-zero value of the angular velocity of the fluid element, while irrotational flow means there is 0 angular velocity of the fluid element. Now, how can we conceive it? How can we picturize it? So, you remember in the last lecture we had drawn a diagram to indicate the angular velocity of a fluid element in a planar sense. So, we had looked at the problem in the xy plane, and we originally defined a rectangular fluid element like this, the 3 corners of which are A, B, C, marked A, B, C, and then we look at the same fluid element after a short time, and we find it like this at a different location based on the u v velocity components which exist at that point of time and at that location. So, we realize that there are angular deflections involved in turning these faces by certain angles delta theta and minus delta theta 1. So, when you look at rotational flow, let us see how the fluid element may be moving along in the flow field. So, you start with a square or a rectangular shape, and one possibility is that it has a kind of a rigid body rotation. The shape as such remains intact, but it just rotates. So, you have a delta theta 2 here, and you have a delta theta 1 here. Remember that the counterclockwise direction is considered positive, and therefore, it executes rigid body rotation where delta theta 1 and delta theta 2 are equal, and therefore, if you look at the omega, then the omega will be like half of 2 times d delta theta dt. So, it essentially accounts for twice the effect because the angles are equal. You may have another situation where the element deforms like this. So, one side remains as it is, while the other tilts by an angle delta theta 1, and therefore, you will still have a non-zero value of omega. In a general case, you will have delta theta 1 not equal to delta theta 2, but both are not equal to 0. So, these are typical situations of rotational flow. How about irrotational flow? We will again start off with an element like this and look at the possibilities. So, one possibility is that it just translates, it is a pure translation, no rotation, which means delta theta 1 and delta theta 2 both are 0. Angular velocity is 0. What could be another possibility where they do rotate, but they rotate in a very special way? Well, that other possibility is this, that you have a rotation of one surface by delta theta and another by delta minus delta theta. So, basically when you sum them, they sum up to 0, which means again your omega is 0. And remember, because you are looking at a planar problem in the xy plane, therefore, when you say omega, it means omega z, the z component of omega only. So, when you have a 3-dimensional element moving in a 3-dimensional flow field, there in principle for rotational flows all three components omega x, omega y, omega z may exist, while for irrotational flow even in a 3-dimensional flow field you have to ensure that all the components are identically 0. So, this is about rotational and irrotational flow fields, and let us add a little bit more before we move on to the next topic, that in a 2D flow field, if you have the situation that the omega z is 0, you can similarly say that capital omega z will also be 0 consequently. The only difference is that half, the factor half goes away, and then this should be 0. What this basically means is that del v del x is equal to del u del y. This is the relation it has to fulfill. Now, rotational flows are seen in boundary layers. We will discuss this in a subsequent lecture. So, these are the very thin viscous layers formed around solid surfaces when a viscous flow moves past a body, and it would be there in general for regions dominated by viscous effects. When you go beyond the boundary layer, the viscous effects still exist, but they become negligible, and there you can by and large assume the flow to be irrotational. Rotationality can also show up in a very different situation in high speed flows, where even if you assume that the flow is by and large inviscid in nature, in high speed flows when there are curved shock waves, there is rotationality in the flow field. That means, the fluid elements can rotate with non-zero angular velocity. We will discuss these kind of flows later in the course. So, that sums up on angular velocity, vorticity and rotational and irrotational flows. Let us next move on to strain of a fluid element. So, we have been discussing about spatial derivatives of velocity components. So, there is something more that is waiting for us to be defined in terms of those velocity gradients, that is called as the strain of a fluid element. So, we go back to that fluid element and we look at those angles which were formed after it underwent angular after it underwent some deformation due to the presence of non-zero angular velocity. So, when we look at it in a planar sense in the xy plane, we can quantify the strain as delta theta 2 minus delta theta 1, which essentially is the total angular deformation. So, originally we started with a right angle here, while now we are at a much reduced angular orientation between the two sides. So, the total angular deformation given by this expression quantifies that, and that is what we call as the strain of the fluid element. Now, in solid mechanics we say that stress is proportional to strain within the elastic limit, while in fluid mechanics or aerodynamics, stress is proportional to time rate of strain, or briefly rate of strain. We have to be very careful about this connection. Going back to the figure that we drew, we recall that we can quantify these angles using derivatives of the velocity components in this manner and using the time interval. delta t. Now, time rate of strain would involve time derivatives of these angles naturally, and since we are in the x y plane, we will define it as epsilon x y. Similarly, you can define it in other planes. So, let us write down the expression for epsilon x y to begin with. So, that will be d theta 2 dt minus d theta 1 dt, where as you may recall that we get these derivative expressions by limiting delta t to 0. And what does it give? It gives us del v del x plus del u del y. So, this is epsilon x y. This gives you the time rate of strain in the x y plane. As we said that in general it will occur in other planes also. So, epsilon y z, how can we write it? We take a clue from this expression. So, the x appears here in the denominator of the first derivative, y in the denominator of the second derivative, and the velocity component corresponding to x appears here in the other term, the numerator of the other term. The velocity component corresponding to y appears in the numerator of this term. So, you need to look at that pattern, and following that pattern, let us try to write it down. Epsilon y z, when we write it down, we will follow this. So, we have done the denominator. Now, the numerator connecting it with z, we should have a del w here, connecting with y, we should have a del v here. That is how we write it. Similarly, epsilon z x so we have written expressions for the strains, the different components of it. So, like you have seen for angular velocity or curl of the velocity, the time rate of strain is also dependent solely on derivatives of the velocity components. Let us write down a matrix comprising of these derivatives. We will fill the first row of that matrix using the derivatives of the u velocity component. Similarly, the second row with v and the third row with w. And we are writing down the derivatives in the sequence of x, y, z. So, in this matrix, if you look at the diagonal elements, you have del u del x, del v del y and del w del z. If you were to sum them up, what do you get? You get del u del x plus del v del y plus del w del z, which in index notation may be written as u del u I del x I, and that is called as the divergence of velocity. So, how do we define divergence through its physics? So, divergence of the velocity, it gives us the time rate of change of volume of the fluid element. This is also called as dilatation of a fluid element. What do we do with the off diagonal terms? The off diagonal terms are the cross derivatives, derivatives like say del u del y, del u del z, or del v del x, del v del z, or terms like this. So, these are all off diagonal elements of that matrix. Remember that these derivatives are participating in the expressions for omega, curl of the velocity vector, and also in the strain. So, the strain rate you already learnt it, it is represented as epsilon. So, in all these the off diagonal elements have participated. Now, we will do a brief recapitulation of some important mathematical tools which include gradient of a scalar field to begin with, followed by divergence of a vector field, and then subsequently we will look at a few integrals, line, surface and volume integrals. So, let us start our discussion on gradient of a scalar field. So, we know that different scalar quantities are of interest in aerodynamics. So, they include pressure, density, temperature, to name a few. There are many more. So, if you take pressure for example, in a 3-dimensional flow field which is steady, then pressure would be a function of x, y, z. It would be function of the location of the point. Now, how do you define the gradient of pressure once you have defined that function? We write it as this. It comprises of 3 components and it is a vector quantity. So, based on the functional form that we have p x y z, you can in principle obtain the partial derivatives of pressure with respect to x, y and z, and they would form the components of the gradient of p vector. So, this is a vector quantity. And if you look at the components, they are talking about the pressure gradient along x, y, z directions. You will see that they would play a major role in the momentum equation later on when we discuss them. When you look at the magnitude of gradient of p, it gives you what? It is the maximum rate of change of pressure per unit length of the coordinate space. Here of course, we are talking about a Cartesian space. You could have other orthogonal coordinate systems as well, like say cylindrical polar coordinates or spherical coordinates. In this case, we are mostly discussing about Cartesian coordinates. So, these are all examples of orthogonal coordinate systems. What about the direction of p? It is the direction along which the maximum rate of change of pressure occurs at a given point. So, if you are again looking at the field in a planar sense, in the x y plane, you could have contours like this, lines which indicate constant pressure. We call them isobars, and let us say they are connected with each other with an inequality like this. So, if you are at a point P here, grad P will give you the direction and along which the maximum rate of change of pressure takes place. If you are looking at any other direction, let us say you are looking at a different direction which is defined by a unit vector S, then a gradient of the pressure field along the S direction could be obtained by taking a dot product between grad P and the unit vector S. So, that gives you what? It gives you a directional derivative. That means, you now find out the rate at which pressure will change as you move unit length along a different direction, which is prescribed by this vector S, which gives you the unit vector along that direction. So, we discussed briefly about gradient of a scalar field. Now, next we will discuss about divergence of a vector field. Few minutes back, you saw the mention of divergence of velocity field when we were looking at the metrics comprising of the derivatives of the velocity components. So, in general, if you take a vector field in the x y z space, we will define the del operator and we will dot it with the vector v. So, when you dot this operator with the vector v, let us say the vector v in general has components v x, v y, v z. Then as you can understand that following the rules of dot product, a term in I will dot with another term in I, producing that component of the gradient of v. So, here that basically becomes del x v x, del x of v x. Similarly, del y of v y when you look at the dot product of the j terms, and then del z v z. So, when it is the velocity vector, we will usually indicate it with the lowercase u v w's. Here the v vector is a general vector. So, we have indicated the components as v x, v y and v z. So, finally, we get a result like this, which as you can understand that if v was a velocity field, we would have written it like this: del u del x, del v del y, del w del z. So, this is essentially the expression for divergence of a vector field v, and as you can understand, this is a scalar. So, gradient of a scalar field produced a vector, while divergence of a vector field produces a scalar. We have to keep these details in mind. And now, we will start discussing about a few integrals, which are going to be very useful for us. So, integrals will comprise of line, surface, and volume. So, let us say we have a vector field V as a function of x, y, z, and we draw two curves within that vector field. One is an open curve, the other is a closed one. So, this is a closed curve, okay, and we are calling the curve as C. We are traversing it in the counterclockwise direction and considering that to be the positive direction, and we are marking a small segment on it which follows the same direction. We mark that component as ds, and over that element, this is the indication of the vector v. So, this is the closed curve, and as we said, this is the open one. So, in the open curve, we have a starting point and an end point A and B. We similarly define a segment on it, and we will define an elemental vector So, that vector will be indicated as the unit vector along the tangent times the length of the vector, which is basically a scalar. So, if you take a line integral, so you are taking a line integral of the vector v along open curve C from point A to B. You will indicate it like this. You show the limits as A and B, while the line integral of V along a closed curve C, like the one we have indicated on the right, would be shown like this. When it is a closed curve, always remember that we are traversing the curve counterclockwise, where the area covered within the curve always lies to our left. So, this is the convention we have to follow. So, we conclude this lecture saying that we discussed about rotational and irrotational flow. We also discussed about strain of a fluid element, and then subsequently the divergence of a fluid element was explained. And then we looked at gradient of a scalar field and divergence of a vector field in the mathematical tool building exercise, and we also initiated the discussion on different kinds of integrals, including line and surface integrals, and we discussed in detail about line integral. So, these are going to be important mathematical tools which we would require all through the course. Thank you.